Okay, so let's start today's lecture. Okay, so we have concluded talking about regression, and we are going to move on to classification. In regression, we realized, at least in least squares regression, we realized that we needed to do like a review of linear algebra, which I did, and hopefully that was helpful to most of you. In As we go through more and more of machine learning, supervised machine learning, we'll see that we need other concepts too, especially from probability theory. So before actually starting to talk about classification, I'm actually going to give a lecture on probability theory background that we will need for, um, this class. So I'll talk about probability theory background. So we'll spend today talking about it, and next time when we start the first lecture on classification, we'll kind of realize that we kind of need it almost right away. Probabilistic modeling is a very important concept in machine learning, and we could also have used it in regression, but we will see very quickly that we will need it in discussing various classification approaches. So let's assume that we have just two random variables for now. We have random variables x and y, and right now I'll just assume that these random variables are discrete, so they take values x1, x2 through xm, and y takes values y1, y2 through yl. So when I have these two discrete random variables, I can actually look at their joint distribution and think of it as a table. So I have joint distribution P of xy, right? And I can represent it, I can look at the table over here. The columns are indexed by the x values or the x random variable. The rows are indexed by y. So the different values that y can take is y1, y2, yj, yl, and x is x1, x2, xi, and xm. Okay. And so, for example, if I am looking for the jth row over here, yj, and the ith column, right? This is, if I want to be very particular, I will say that this is P probability of x equal to xi and y equal to yj. Okay, and many times we don't want to have such a cumbersome notation, and we'll just say that this is probability of xi comma yj. Okay. And now suppose, I have dealing with these random variables that can take these discrete values. I can kind of have n trials. Okay. And in the n trials, I can record nij as the number of times in these trials we observe that x equal to xi and y equal to yj. Okay. And as I start doing more and more trials, that as n tends to infinity, what this is that pxi yj will be equal to, so this estimate will converge to the actual probability values. Okay. So when we are talking about random variables, there are two important concepts that are important. One is called the marginal distribution. So even though I have a joint distribution, I might be interested in what is Px equal to xy. So I'm marginalizing over all the y outcomes. That's why this is also called as the marginal distribution. Okay, and that is going to be just the summation. Okay, so remember the y takes the values y1 through yl. So I look at P of x equal to xi, y equal to yj, right? And I actually sum over, sorry, this should be j equal to 1 to L. Okay, so I'm marginalizing over y, and I get the marginal distribution P of x equal to xy. And now if I look at kind of the details about what it is, right? This is going to be a summation of j equal to 1 through L. If I have n trials, right? This is each of these values, remember, is ni j divided by n. Okay, now n is kind of a constant, so I can get it outside. And then summation of nij I can call as ci. Okay, so for example, over here in my table over here, if I record the number nij in each cell, right, then I can actually list the kind of cumulative sums as C1, C2, CI, CM. Okay, and clearly CI is equal to the sum along this entire column, right? So summation of Nij, where my j is going from 1 through L. Okay, and that's what's coming out over here. So this turns out kind of gives you one important rule, okay, which is kind of the sum rule. And then the other than marginal probabilities, an important concept is conditional probability. Okay, so conditional probability. So suppose I'm looking at the conditional probability of y equal to yj, given that I've already observed that x equal to xi. Okay, and that will be denoted by P of y equal to yj, given that x equal to xi. Right? And if you think about the table over here, right? So this is kind of saying that you are now only really concentrating on this part of the joint distribution. You're looking at that x is already given to be xi, and then what is the probability then that I get this? So instead of being nij divided by n, that is the probability of xi comma yj given n, it'll be nij given by the divided by the marginal distribution, right? So it's actually going to be equal to nij, sorry, nij divided by CR. Okay, and just like we, had this more concise form for the joint distribution, we'll also write this as P of yj given xi. So what we see is that P of yj given xi is nij divided by ci, right? As, of course, the number of trials becomes larger and larger. And so let me just write that again, P of yj given xi, okay? Oh, sorry, remember the joint distribution, P of yj comma xi is equal to ni divided by n, okay? Nij. And I can say that this is equal to nij divided by ci times ci divided by. So it's still nij divided by by n, but now I've written it in terms of Well, the conditional distribution and the marginal distribution. So if you like, again, let me kind of just write this out. P of y equal to yj, x equal to xi, right? This is equal to, over here, this part, right? Which is the same as this part over here. Okay, so this is equal to P of y equal to yj, conditioned on x equal to xi. And this is the marginal distribution. Remember, we saw this above. This is P of x equal to xi. Okay, so this is P of x equal to xi. Okay, so this is often known as the product rule. If you, for example, take a look at the book by Chris Bishop, then he will also have a section devoted to this. This is the product rule. Okay, so just to summarize, right? I have two rules. This is the sum rule. I'm just writing it now in terms of the random variables. Right? You get the marginal distribution by marginalizing or summing over all the y outcomes. Okay, so this is the sum rule. And then we get the product rule. P of x comma y is equal to P of y given x times P of x. This is the sum rule, and this is the product rule. Okay. Now we could have conditioned either on x or we could have conditioned on y. Right. So if I look at P of x comma y, right, what I've written above is that I have this equal to P of y given x, P of x. But I could easily have conditioned over the other variable first, right? So I could have written this as P of, I can write this as Px given y times Py. Okay, and that gives us the famous Bayes rule. So this is used a lot in machine learning, especially when you do probabilistic machine learning, right? So Bayes rule is that if I want to compute Py given x, okay, I will basically write this. So remember, Py given x is over here. Okay, so this is something that I want to compute. Then I can write this as Px given y times Py divided by Px. P of x given y times Py divided by P of x. Okay, so many times this is known as prior. So for example, we'll see that, suppose we want to look at like classification of an email into spam or not spam. In that case, y is a discrete variable that takes values either in spam or not spam. And then there might be a prior distribution that, hey, maybe most emails are actually normal and not spam. And so Py equal to spam might be much lower than Py not equal to spam. So that's something that we can either guess from the data, or we may have some reason to give a kind of different prior. And this is known as the posterior. So in the email example, the X might be, some kind of data, right? So XI, YI pairs. And what you want to know is the posterior, which is given the data, what is the probability that it is, that the email, for example, is spam or not spam. But what really helps us in making the decision is P of x comma x given y, right? So that is known as either the evidence or the data likelihood. So for example, which will model, right? Given the spam emails, what do the spam email distribution looks like? Given normal emails, what are normal emails look like? Okay. And if you notice over here in the denominator, we have P of X, right? That's the marginal distribution, and I can actually substitute PX over here, right? So I get that this is equal to Px. So this is the numerator as above, Px given y times Py, and then the summation over y, which is P of x comma y. Okay, and I can now write the denominator as, again, this, and I can apply the product rule over here, and I can say that this is P of x given y, Py. Okay, so you can see that the numerator is one particular x equal to x, and the denominator is summing over all the particular y's. Okay, so that is Bayes' rule that comes up quite a lot. So I've given you like a very quick introduction. So let's actually look at a particular example. Okay. So, but before we do that, just one kind of notion which comes up again quite a lot is the notion of independence. Okay, so two random variables are independent of each other if pxi comma yj can just be factored as pxi times pj, p of yj. So just in terms of the marginals, and you don't need any, it actually is the joint distribution is like the product distribution of the marginals. So for example, and in particular, this implies that P of yj given xi is just equal to P of yj. So it doesn't really, the conditional distribution is, does not depend actually upon xi. Okay. So this is kind of the notion of independence. Let's take an example that illustrates many of the above things, right? And how we can infer some probabilities given this information about the joint distribution or the marginal distribution. Okay, so let's take an example where we have two boxes. Okay, so we have two boxes. This will be blue and red. And we have two types of fruit. This will be apples and oranges. Okay, so let me draw like a red box. So I have a red box. Okay, and then I have a blue box. Okay, and suppose somebody says, hey, we are given that, the probability of choosing the red is going to be 0.4, which is 2 divided by 5, and the probability of choosing the blue box is 0.6. The probabilities should sum up to 1. So this is 3/5. Okay, and now suppose I have in the red box, okay, suppose I have 2 apples and 6 oranges. And suppose in the red box I have 3 apples plus 6 oranges. Okay, so the orange color is here. So oranges And I guess I can have, why should be, well, let's go with green. Let's say, suppose they are Granny Smith apples. Green apples. Okay. So just to draw it, we have two apples over here. And then we have how many oranges? 6 oranges. And then the other one, actually in my notes, I don't want to get change things too much from my notes. I think we have 1 orange. We have 1 orange. And we have 3. Okay, so what is the probability of an apple given red box? Okay, come on, somebody help me out.
1/4.
Is 1/4, right? So that's 2 divided by 8. There are 8 pieces of fruit in the red box. Somebody be ready. In the red box, we have oranges. Somebody else? Oh, you want to communicate by chat. Okay. Rishabh says 3/4. Okay.
That was wrong. I was thinking about the last problem. I saw the red arrow. I confused the numbers.
Okay. But is this not correct? Probability of orange given a red box is not 3/4?
Oh, that is, yes, that is.
It is 3/4, right? Yeah. Okay. So this is 3/4. Okay, somebody else, probability of apple given a blue box. Somebody I haven't heard from so far in class.
3/4.
Sorry, could you just repeat that?
3/4.
3/4, right? Probability of apple, green apple, given a blue box. Okay, so there are 3 apples out of 4, and then probability of orange given a blue box is
1/4.
1/4. Thank you. Okay, so now I can start writing this now in a 2-dimensional table, right? Just like we had for X and Y. So let's suppose my box is the one random variable, fruits is another random variable, there's a red box, there's a blue box, there's an apple, there's an orange. Okay. Now, do we know the joint distribution? What is, so let's suppose there are 4 things, right? P of A comma R, P of joint distribution of orange and red, joint distribution of apple and blue, joint distribution of orange and blue. So somebody wants to tell me, give me the formula for PA comma R. Let's suppose we apply Bayes rule.
Is PA times PA given R.
P times A. Did you say?
PA given R times PR.
Perfect. I can also have written it as P of A, P of R given A. Let's come to that later. But we know this, right? P of A given R is what? 1/4 from above. And P of R is 2/5. So that is 1/10. What is P O comma R? The joint distribution. Similarly, P of O given R times P of R. Okay, P of R is 2/5 as before. And P of O given R is 3/4. So that becomes 2 is equal to 3 times. Now, what about this part? Is this formula wrong or right? It is correct, right? But do we know what P of A is? Actually, we don't, right? It's not kind of straightforward because the process involves picking the box first and then picking the fruit from the box. Okay, but we will try to infer that, right? We'll try to see that the sum rule and the product rule will allow us to figure out what P of A is and what P of R given A is. Okay, but meanwhile, we have P of apple given the box is blue. Again, apply P of A given B, P of B. Okay, P of B is 3/5. And P of A given B is over here, 3/4, right? Okay, so that becomes 9/20. And P of orange given blue box, P of blue box. P of blue box is 3/5, and this is 1/4. So this is 3 divided by. So I can start filling actually this joint distribution table, right? So PA comma R is 1/10. The O comma R is 3/10. This is 9/20. And this is 3/20. And you should verify that we were given that P of R is 2/5, right? So if I add these two up, right? If I add P of R, A comma R plus P of O comma R, what does it add up to? 4/10, which is 2/5. Right? And that's P of R. And you can see that that's exactly what was given away. So far, I haven't made a mistake. Okay. And this is P is 12 divided by 20, which is equal to 3 divided by 5. And this is P of, and you have verified that this is the same. Okay. What about probability of picking an apple now? Okay, somebody? Remember that that's not right in front of us, right? So we actually have to do a marginalization, right?
So we add up the PAR and PAB.
Yes, so it is PA comma R plus PA comma B. And that is 1/10 plus 9/20. And that's equal to 11/20. Okay, so that's this sum. And what about P of O? Well, P of O is P of O comma R plus P of O comma B is equal to 3/10 plus 3/20, and that is equal to 9/20. We could actually have also gotten it from here, right? It's basically 1 minus 11/20 is equal to 9/20. Okay. What about, let's say, this thing that we were talking about, P of suppose you you observe that you've picked an orange. Suppose you're observed, you have picked an orange. What is the probability that you pick the, you will pick a red box given orange, right? So again, we can apply Bayes rule. So that is P of O, comma, given R, P of R divided by P of O. What is P of O given R?
3/10.
3/4, right, over here?
Oh, sorry, yeah. Sorry, I meant 2/4. Yeah.
Yeah, P of O given R is 3/4. Remember, if you have a red box, then there are 6 oranges out of 8. So that's why it is 3/4 times. Oh, I could also have written this. Oh, it's okay. What is P of R? P of R is 2/5 divided by P of O, which is 9/12. I could actually have just, said that this is equal to P of O comma R. And I'd already done this, so I kind of repeated it, but it's okay. Right? So this is equal to, it's the same as this quantity over here. Right? This is the same as this. Okay. So that is equal to 3/10 over 9/20, right? So that's equal to 310 times 20 by 9, and that's equal to 2/3. Okay, so you've seen like that, it's all very consistent now, right? If you have the sum rule, and then you have the product rule, and they give us the very important Bayes rule. Any questions so far? Okay, we've talked a little bit about discrete random variables right now. So let's talk a little bit about probabilities with continuous variables, and then we'll talk about the ubiquitous Gaussian distribution that comes up a lot. Okay? So, and we'll talk about the multivariate Gaussian distribution, which some of you might have seen, some of you might not have seen. Okay? So probabilities with respect to continuous variables. Okay, so we'll have X belongs to R. So right now, just let's take, well, we can take either X belongs to R, or later on, we'll see that we'll actually look at where the continuous variable is D-dimensional. Okay. So we have, we have something called the PDF, which is the probability, sorry. Probability density function. Okay, and we denote it by a capital of px, little px typically, right? And it's a function, it's a continuous function. P of x is greater than or equal to 0, right? And it adds up to 1. So what does it mean for a continuous variable? It basically is that the integral, suppose the domain is -infinity to +infinity, then the integral is 1. So that's the analog of the sum of the random of a discrete random variable. Okay, so similar to the sum rule and the product rule that we had for continuous for discrete random variables, we have the sum rule, which is that the marginal distribution is when we integrate out the other variables. So suppose we have a two-dimensional joint distribution between x and y, right? We marginalize over y. So that's kind of saying that we analogous to summing over all the different possible values of y. And my product rule is that my joint distribution is the conditional distribution times the marginal. So this is contained conditional distribution given x, and or you can do px given y times p. Okay. So, you know, I didn't talk about it really in terms of in the discrete case, but you know, you have the mean of a random variable, right? So expectation or mean, okay? That is, so suppose I have a function of a random variable f of x, then I have, in the discrete case, it would be, sorry, maybe I won't write it here, the discrete case, but this is going to be integral of p of x times f of x dx. Okay, and in the discrete case, it would have been summation of x dx of x. Okay, in particular, I have that the expectation of the random variable is equal to x dx dx. Okay. In addition to expectation or the mean, there's another important concept called variance. Okay. By the way, note that expectation has this property that expectation of x plus y is linear. Is expectation of x plus the expectation of y. And you can see that easily from the integral, because the integral will become, the one integral will become the sum of two integrals. Okay, so now suppose again I have a function of x, f of x. Okay, my variance is going to be the expected sum squared deviation from the mean. Okay, so I said a lot. So expectation, that's the first part. Square deviation is f of x from the mean. Mean is expectation of f of x. Okay, square. Okay, now if I take the quantity within the brackets, if I open it up, I get f of expectation of f of x square plus, I'll, you know, it's basically a minus b square, right? So I have a square plus I have this mean of f of x. Just be careful where you put the squares and where you put the brackets, right? Minus I have 2 of this part, which is f of x times this part. F of x times expectation of f of x. Okay, and remember, since expectation is linear, I have expectation of f of x square. Okay, plus I have expectation of f of x. I'm just expanding out things. Okay, I could probably go quicker, but I just want to show all the steps. Right, so 2 of, I have expectation of f of x times expectation of f of x. Okay, this first part remains the same, f of x. Okay, the next part is basically expectation of expectation, which is a constant. So I get rid of the outer expectation or inner expectation, whatever you. Okay, and then over here I have 2 times, this is kind of a constant, so I have expectation of f of x appearing times the expectation of f of x, right? So 2 times expectation of f of x appearing twice, right? So these two give me expectation of f of x square minus I take the expectation of f of x, and then I square it. Okay, so very important to notice where the squares are, right? So the square inside is inside the expectation, and here you are taking square of the expectation. Okay, so in particular, you probably have seen this formula in a course in statistics, that if you have a variance of x, then it is expectation. If I go back to this original formula, right? I've just replaced f of x is the identity function. So it's expectation of x minus so it's a deviation of each observation, x, from its mean. Okay, so it's x minus e of x squared. And like what we did above, you can go through all the steps in particular for this, but we've already done this above. This is expectation of x squared minus, you take the expectation and then you square it. Okay. In addition to variance, when we have two or more random variables, and in particular, for example, if I have a two-dimensional random variable or a d-dimensional random variable, another thing that comes up is the covariance. Okay, and many times we'll use cov as to denote the covariance. So the covariance of xy is basically how they kind of behave from the deviation from the mean. So x minus expectation of x. Sorry, let me be a little careful. Times y minus expectation of y. Okay. And then if you again kind of go through the similar exercise as before, what you will find is that this is expectation of xy minus expectation of x, expectation of y, right? So covariance of x with itself is just going to be the variance. And that's what you'll get. You'll get expectation of x squared minus expectation of x whole square. And that is if x equal to y. Now, we've noticed, we talked about a little bit about independent random variables, right? So what if x and y are independent? Okay, if that's the case, then I have p of x comma y is equal to px times py. So if I have covariance of x comma y, remember the covariance of x comma y is x expectation of xy minus expectation of x expectation of y. And if you think about what this is, right? This is basically p of x comma y times xy integral dy dx, right? And if this breaks up into px py, I can write this as xpx times xpy. Okay, and that's expectation of x times expectation of y. Okay. And if I do this, then what do I get? That covariance of xy is equal to expectation of x times expectation of y minus expectation of x times expectation of y. So it's equal to 0. Okay, if x and y are independent. Okay, so the covariance is 0 if my two variables are independent, right? So covariance of xy equals 0 if x and y are independent. Okay, now let's talk a little bit about Gaussian distribution. And what my goal is to tell you what a multivariate Gaussian distribution is, right? I don't know how many of you have seen that. Almost all of you have seen, I'm sure all of you have seen what a univariate Gaussian distribution is. Okay, so let's start with that. But we will, by the end of class, we will talk about the multivariate Gaussian distribution. Okay. So I have a Gaussian distribution. Okay, and that's also called the normal distribution. Okay, so we'll assume in the univariate case that X belongs to R. Okay, and the Gaussian distribution X. Okay, so there are two parameters in a Gaussian distribution, mean and variance. Okay, so given particular X and sigma square, and many times we'll just, not write the given part, we'll just say P of X or the PDF is given by this particular formula. 1 divided by square root 2 pi times sigma e to the power minus half x minus mu square divided by sigma square. Remember that mu is the, well, not remember, but mu is the mean or expectation. Okay, and sigma square is the variance. So for example, if you take this PDF and you actually calculate the integral of x times px, you will get mu. And if you compute the integral of, that corresponds to the variance, then you will get sigma square. Okay, so in particular, x px dx minus infinity to infinity is equal to mu, which is the expectation of x. And then if you compute expectation of x minus mu square, remember this is the same as expectation of x square minus mu square. Okay, that's expectation of x square. This is equal to sigma square. So that I'm pretty sure that all of you have seen. But now let's move to the multivariate case. So now suppose I have x, which is a d-dimensional vector. Okay, so x has multiple components, x1, x2, xd. So I think you should be able to clearly see that if I do expectation of x, that's going to be expectation of mu1, x1, which is mu1. Let's denote that by mu1. Expectation of x2, which we denote by mu2. And expectation of xd, which we denote by mu d. And this we'll call as mu. So remember, mu is a vector. Mu belongs to Rd. Okay. And let's just look at the univariate variances, right? So if I look at xi minus mu I square, let's say these are sigma I square. Okay, so there are d of these variances for each component of the vector. But what we are interested in is a joint modeling. So remember, x is an Rd. So really x is a vector. So the joint distribution of x is, so if I think about the kind of notation we had before, that's it. We are looking for the joint distribution of each of the components of the vector x. So what is the multivariate Gaussian distribution? Well, instead of going straight to the Gaussian distribution, let's take a simple example first. And then we will extend it to the multivariate Gaussian distribution. So let me first let's assume that the xi's are all independent of each other. Suppose xi is independent of xj for all I not equal to 2. Okay, so they're all independent of each other. And we know that the joint distribution in that case is just the product. Okay, so maybe I'll just write it in case you're not familiar with this notation, but it is P of x1, P of x2, P of xd. That's the product of this, and that is denoted by the symbol, which is the product for I equal to 1 to d of P of xi. Okay, and now let's write it out, right? What is P of xi? Well, xi is it's a Gaussian distribution. And we saw that this was the formula for P of xi. So P of xi is going to be 1 divided by square root 2 pi sigma 1 times e to the power x minus mu 1 divided by sigma 1 square, right? So so this will be 1 divided by square root 2 pi times sigma 1. But let's just look at this thing which is before the exponential, right? How many times will it appear? There are d times, right? There are d terms over here. So this will appear d times, and then this will be sigma 1, sigma 2 to sigma d. Okay, and then the thing within the exponential, it will be a product of e to the power, so same as here, I'm just rewriting it down over here, e to the power minus 1/2 of x I minus mu I square divided by sigma I square. And the product is from I equal to 1 through d. Okay, so I will rewrite this as 1 divided by 2 to the power I d by 2. I haven't really done anything. I just take the square root, right? Written it as power half and written it like this. And then I have sigma 1, sigma 2 to sigma d. Okay. And now you need to notice one thing. This is the product of exponentials, right? So if I have e to the power a times e to the power b, that's equal to e to the power a plus b. So what happens is that I can basically turn this product into a sum if I take it into the exponent. So this becomes e to the power minus 1/2 summation of xi minus mu I square divided by sigma I square. Any questions so far? And remember, the summation is I equal to 1 to d. So what I can do is I can actually take a matrix sigma. By the way, sorry, because I don't think I can avoid it, but this is a matrix sigma. Okay, whereas this is the notation for a summation. Okay, but I'm actually collecting things in a matrix sigma, which is sigma 1 square, sigma 2 square, sigma d square. So it's a diagonal matrix with the variances on the diagonal, and everything in the off diagonal is 0. What is the determinant of this matrix?
like the products of the diagonals.
The determinant of this matrix is the product of the diagonals. So it's sigma 1 square, sigma 2 square, sigma d square. So it's sigma 1, sigma 2 times sigma d square. Okay. So this means that I can write this as 1 divided by 2 pi d divided by 2 times the square root of the determinant. You remember the determinant is a number. Is that clear? Okay, and now what about this term over here? This term here, xi minus mu I square divided by sigma square.
Maybe you can turn like xi and mu I into vectors, and you can multiply them by, you cannot take like the dot product of that, of the vector minus like, the x vector minus the mean vector squared. You can take that vector and you can multiply it by the inverse of the sigma matrix.
Okay, yeah. So let's go through it slowly. So suppose I have x minus mu transpose times x minus mu. Okay, remember now x minus mu is a vector, huh? X minus mu is equal to xi minus mu I, sorry, x minus mu is a vector, and that is x1 minus mu1, x2 minus mu2, to xd minus mu2. So if I write x minus mu transpose times x minus mu, that is, well, you can see it's going to be the sum of the squares, right? So the summation of I, xi minus mu I squared. So it's starting to look a little like this, except I don't have sigma I square, okay? So then if my sigma is diagonal, x minus mu transpose times sigma inverse x minus mu is summation of I, xi minus mu I square divided by sigma square. Okay, and remember that sigma is diagonal. Let me just write it again, right? Sigma 1 square, sigma 2 square, sigma d square. This matrix sigma L diagonal. Okay, I apologize because you have to realize that there are two sigmas out here, right? So just by context, this is the matrix of the variances and this is the summation sign. Okay, it's I equal to 1 to D, I equal to 1 to D. Okay, so this says that my joint distribution in the case when I have independence between xi's is, I can write it as 1 divided by 2 pi d divided by 2 determinant of sigma to the power half times e to the power of minus 1/2 x minus mu transpose sigma inverse x minus mu. Okay, so I just wanted to kind of just show you that in the case of independence, I can write it like this. Okay, now let's look at the general case. General case. Okay, in the general case, I'm not assuming that the xi's are independent. So I have x belongs to RD. Okay, and let me So I have a multivariate Gaussian distribution. Okay, and the PDF, what's it given by? Well, guess what? It's going to be identical to this, except sigma will not be, the matrix sigma will not be diagonal. So 1 divided by 2 pi, b by 2, determinant of sigma to the power half, e to the power minus 1/2 x minus mu transpose sigma inverse x minus mu. Okay, and where as before, mu is the mean. That is, mu is equal to expectation of x. Okay, and that's just the same as before, mu1, mu2, to mu d. Mu I is equal to expectation of xi. Okay, but my matrix sigma is the, remember earlier it was the diagonal matrix with variances on it. But in general, it'll be the covariance matrix. That is, it's defined to be expectation of x minus mu transpose. And in particular, sigma ij is the covariance between xi and x2. Okay, so the covariance matrix has the following property. Remember, it is going to be a D by D matrix, right? That's pretty easy to see. It is going to be symmetric. Okay, and is also positive definite. Remember what positive definite means? That it is all the quadratic form is greater than equal to, all quadratic forms are greater than equal to 0, which means that the eigenvalues of this matrix are all, they're not only real because it's a symmetric matrix, but they're also greater than 0. So that means if I have sigma is V lambda V transpose, right, which is the eigenvalue decomposition. The only set of matrices for which eigenvalue decomposition and the singular value decomposition are identical are the positive definite matrices, positive semi-definite. It's either you can call it the SVD or eigenvalue decomposition, so lambda is diagonal. Okay, lambda II is greater than 0, and the matrices V are orthogonal matrices, right? So they are the orthogonal matrices, matrices where the columns correspond to the eigenvectors of sigma. And then what happens? So we have sigma inverse here in this formula. Okay, so sigma inverse can be written as V lambda inverse V transpose. Okay. And so the quadratic form half of x minus mu transpose, thing that appears in the exponent of the Gaussian distribution over here. Okay. That I can write as half x minus mu transpose V lambda inverse V transpose x minus mu. Okay. So what I can do is I can actually form another variable, z, which is equal to this. So maybe I won't do that. Sorry. Okay. Let me just kind of use a different color. And let me say that I'll make this equal to z. Okay. So I have z is equal to v transpose x minus mu, which means that half of x minus mu transpose, just from copying from above, is equal to 1/2 of z. Oh, my 2 is starting to look like a z. Oh, sorry. Okay, it's equal to 1/2 of, I don't think I made it any better, but it is z. Let me try to write it. Z transpose lambda inverse times z. Okay. And if you notice, like, if I just ask you, like, what are the contours of equal probability density, then this will be P of x equal to C, which is that, so it implies that, you know, I have half of Z transpose lambda inverse Z is equal to some C prime. Okay. And if you think about it hard enough, or you can just expand it, you'll see that this is equal to summation of zi square divided by sigma I square, where lambda is, well, let me call lambda is equal to lambda 1 through lambda d. Okay, and in this case it is lambda d, right? But remember that lambda I. Remember that lambda i's are all greater than or equal to 0. So this is this. And if you know, this is just the equation of an ellipse. Okay, so what that means is that in Z, right, and this is ellipse centered at 0. Okay, so this particular case is, you know, P of x equal to some C. Okay. The reason I'm drawing it is that many times when you see a Gaussian distribution, you will see the following picture, which is that, and when you look at things like principal components analysis that you might have heard about, right? You'll actually see a picture like this. Not the same as what I've drawn over here, because this is centered at the origin, right? Sorry for the bad picture, by the way. This is supposed to be, these are all supposed to be symmetric ellipses. Okay, so let me see if I can draw it a little bit better, or similar figure, not centered at 0 and not axis parallel, right? So whenever you see things like PCA or so, you'll see, maybe I'll draw it below. You'll see something like, you know, there's a center over here. Well, I don't know if my drawing is any better, but, you know, this is V1, this is V2. And remember, I'm drawing it in 2 dimensionals, but there are D orthogonal vectors over here, right? So this is P of x equal to C. And why is this kind of, you know, so this is going to be mu. Okay. So if you notice that my transformation was this, right? So that kind of said that I made the origin equal to 0. And then I did the orthogonal transformation. So when I undo that, I get this. So this is sometimes how the PDF or, you know, contour plot of PDF of Gaussian. Okay. And these sigmas are supposed to represent, so these ellipse, this ellipse, in some sense represents the covariance matrix, right? It would be these would all be circles if all the singular value or eigenvalues were identical, right? So the special case is that if all if, for example, it was like this, right? Then this is kind of saying that my sigma is diagonal, right? And that all my eigenvalues are equal. So for example, when you draw from a Gaussian, which is, unit variance in each dimension, all the variables are independent, then the covariance matrix would be equal to the identity. Okay, so this is the contour plot of PDF of multivariate Gaussian. Okay, any questions about this? So, so just to recap, I started off by, come somewhat slowly, talking about discrete joint distributions, discrete random variables, and we saw that there is a sum rule and a product rule, and then we can extend it to probabilities, probability density functions where we have continuous variables, similar concepts, mean, variance, sum rule, product rule, and then we saw a particular case of distribution, which of course is ubiquitous, the Gaussian distribution. Now, many books will give you this particular formula directly, and they'll say that, hey, this is the mean and this is the covariance matrix. But I wanted to build intuition, right? So we showed that in the case where because many of you have seen the univariate Gaussian distribution, right? That if the variables are identical, then you can write the PDF of this in the same way as you write the PDF of a general multivariate Gaussian. Of course, sigma is special over here, it's diagonal, right? And remember that earlier we also showed that when X and Y are independent, where did I show it here? When X and Y are, when Xi and Xj are independent, then the covariance of Xi and Xj is equal to 0. Okay, and so you can kind of make sense of why sigma is diagonal over here. In general, it is the expectation of the covariance. In general, it is a d by d dense matrix, and you can represent the PDF like this. And when we come to, we'll probably briefly mention the principal components analysis. That's going to be kind of finding the principal components, which are V1 and V2, which are, some books will say it's the direction of maximum variance of the data. Okay, so with that, kind of we conclude this, again, background lecture on probability theory. And so from next time, we'll start talking about classification, and we'll see how the modeling that we did, for example, today, will straight away come in the next lecture. Any questions? Okay, if there are no more questions, then we conclude, and we will meet on Monday. So remember, there's a homework. Hope you have a good weekend. And then from Monday onwards, we'll start talking about classification. See you on Monday. Huh? Thanks. Bye.